Joel, go for next.
Clear.
Now we move to our session 10 of our faculty development program. This important session is on decarbonizing the atmosphere using carbon capture, utilization, and sequestration, challenges and opportunities, to be delivered by Professor Akshay Ranjan Paul. He is a professor and head Department of Applied Mechanics at Motilal Nehru National Institute of Technology, Allahabad, Prayagraj. Professor Paul brings us with him over 2 decades of distinguished teaching and research experience in areas such as fluid mechanics, aerodynamics, biofluid dynamics, CFD, and green energy, with more than 200 published research papers, 5 textbooks, and supervision of over 60 masters and 8 doctoral theses. He has significantly contributed to both academics and research. He has also been the recipient of 12 research grants from prestigious national and international agencies, further underlining his impactful contributions. We are privileged to have him with us today and look forward to his expert insight on one of the most pressing challenges in the fight against climate change. We extend a very warm welcome to you, sir, and request you to take us through your expert lecture. Over to you, sir.
Make him co-host.
Yes, sir.
Yes, sir. Screen has come. You are visible.
Yes, sir.
Participants are requested to mute, please. Sir, you can start your lecture. Sir, your audio is not coming. Sir, you are muted.
Yeah. Now it is okay?
It's okay.
Okay, good. So, thank you, the organizers, for inviting me to share my thoughts with you regarding energy and environment. So, I'm happy to see around 200 participants waiting in this evening for the talk. Today, I will discuss about decarbonizing the atmosphere using a relatively new technique known as carbon capture, utilization, and sequestration, or in brief, CCUS. And we'll explore the challenges, opportunities, and policy implications in Indian context. If time permits, I will also show you some of the simulation studies carried out by my PhD students who has recently received the degree. So if you see where the global carbon dioxide emissions, so 2024 data says that it is around 40 billion tons, and that is generated by different anthropogenic or human-centric activities, which is all-time high. And therefore, we need to move for a carbon neutral technique to carbon negative technique. And various techniques we know which are carbon neutral, but this is the high time when we should move from carbon neutral technique to carbon negative technique, means employ a technology which is giving you a carbon negative scenario at the end. And carbon negative technology, any carbon negative technology, it is far more challenging, and The most unfortunate part is it is still mostly in their developmental stage. For example, if you see CCUS, we cannot truly say the CCUS is carbon negative. But if you see different CCUS technologies, the technology readiness level at global stage, it is around 6 to 7, whereas in India, most of the CCUS technologies,
అయితే
most of the CCS technologies are around 4 to 5 TRL. But it is expected that worldwide carbon negative technologies, including CCUS, will be implemented between 2050 and 2100. So within the next 20 years, the carbon negative technologies will be in full swing and will be under implementation. Two things I must mention that IIPC report stresses the limiting global warming within 1.5 degrees Celsius. So therefore, decarbonization is an essential one. Another thing is that in Paris Treaty, India signed with a commitment that India will become a net zero by 2070. So obviously, we need to reduce the dependence on fossil fuel and boosting renewables. Professor Gonchavuri has already focused on the renewable part. Now come to slide 2. What is CCUS? CCUS involves capturing CO2, carbon dioxide, the most potential greenhouse gas, which heats up the atmosphere from large point sources, or it can even capture the carbon dioxide directly from air. Then either use the carbon dioxide for some industrial processes or store it safely underground for years, aiming to reduce the emission and to combat climate change. So there are three major components under CCUS. One is capture part. So you capture CCUS from industrial sources, or if you use direct air capture technique, DSC, so you can capture the carbon dioxide which is historically stored in the atmosphere. Next is utilize the carbon dioxide. If you can use the carbon dioxide to transform it into some useful product, so this is commercially beneficial and offset some of the cost of CCUS. Else, you store it securely underground. In the second half of lecture, I will focus more on the storage part, mostly sequestration part. In the first part of my lecture, I will focus on capture, utilization, both. If you see the key sectors playing a role in carbon dioxide emissions in India, this is a 2030 projection. So our power or electricity generation sectors, they takes a lion's share, followed by industry. And in this industry, there are few hard to abate industry like steel, uh, cement sector, fertilizer sectors. So this comes under industry and known as hard to abate, because the problem is that it's very difficult to remove the carbon dioxide from their process. Steel technologies are under development for this hard to abate sector. Next is transportation sector, which emits a lot of carbon dioxide locally, especially in the metros. Then residential. With the rapid urbanization in many tier 3 and tier 4 cities in India, even towns in India. So the villages are not villages. Almost all the houses are built up in concrete. So huge concretization is there, and it also plays a role in emitting carbon dioxide and agriculture. So these are the five major sectors playing a role in emitting carbon dioxide in India. Now, I'm talking about the carbon neutral versus carbon negative technology. So I will get a chance later stage and I will discuss about it. But a few things are very important, like if a straight question is asked, like whether CCUS is a carbon neutral or carbon negative or both. So I must tell that it depends on the situation. It depends case to case basis, like which technology you use for CCUS. For example, if you use a closed loop uh, carbon technology where CO2 is captured, then utilize it to make some product, and then carbon dioxide is recycled, then you may call it as a carbon neutral. And it can be carbon negative if you combine this CCUS with some negative emission technologies. Right now, it is direct air capture or like bioenergy with carbon capture and storage. So it is dependent on which technology you are using, but like direct air capture, it is still being developed in a nascent technology, and the cost is prolific, prohibitively costly. So you cannot really induct it for the industry. Now we'll explore some of the innovative solutions to reduce carbon dioxide emissions and foster um, a greener future. If you see the carbon dioxide emissions in India, few sectors I told you is branded as hard to abate, like cement, steel production units, chemicals, shipping, aviations. So these are known as hard to abate sectors. These sectors are really very difficult, challenging to decarbonize because of their heavy dependence on fossil fuel. And nowadays, steel companies are trying with hydrogen. Hmm. They, they are using hydrogen in the steel process to make it decarbonize. Sweden is the first country to decarbonize the steel production with hydrogen. Indian steel making companies, they are still doing research with help of fundings, in-house fundings, as well as fundings from a few countries like Australia. Another thing is like all these hard to abate sectors are really energy intensive process. Next one is like there are a lot of technological and financial challenges. Whatever technologies are developed, that is really not cost effective. So there is a prohibitively costly. So these factors combinedly made these hard to abate sectors, and India, is still a developing, considered as a developing economy, and we need to at least use carbon carbon intensive economy for at least 20-30 years more, so that we can achieve a GDP growth at our desired level. So we cannot really stop using coal or fossil fuel, other fossil fuel. So here lies the importance. If you want to use coal or fossil fuel, the conventional fuel, so try to use CCUS so that the the loading on climate should be manageable. Now we'll see some of the carbon capture technologies which are established or still being developed. Uh, One is your post combustion capture. So in post combustion capture, you see the schematic diagram on the left hand side of my slide, where CO2 is captured from the flue gas or exhaust gas, which comes after burning fuel in the boiler, and we extract CO2 using some chemicals. But post combustion technology is really energy intensive, and advantage is that out of these three technologies, post combustion technology is most matured. It has high technological readiness level, so you can really use it for any existing plant. Next is pre combustion. So you put a air separation unit before going for combustion to separate CO2. It is common in power plants and hydrogen production, especially when you use a syngas. So for syngas scenario, it is very common because syngas, it is a hydrogen and carbon dioxide mixture, and you just take out carbon dioxide uh, at pre-combustion stage so that you can use hydrogen. And another one is oxy-fuel combustion. In oxy-fuel combustion, what happens? You burn fuel with pure oxygen, no air, with pure oxygen. To create, I request one of the participants to please mute because background noise is coming. I request one of the participant to please mute. Okay, thank you. So in oxy-fuel combustion, what happens? You burn fuel with pure oxygen to create a carbon dioxide rich gas, and that is easier to capture. So these are the three carbon capture methods. Apart from that, there is another method known as carbon negative methods, direct air capture, where you can remove carbon dioxide from the ambient air, thereby addressing both ongoing as well as historical emissions. But there is a challenge. The challenge is that this direct air capture technology is still in its early stage. The cost estimate is like to extract per ton of carbon dioxide. The cost is around US $400 to $800, and its operational scalability is yet unestablished. Okay, so DAC is useful if you capture from large point source. For limited sources, DAC will not be cost effective at all. Now we'll see different CO2 separation technologies. One is like chemical and physical absorption. In chemical and physical absorption, you see different chemicals are used. Now, chemical absorption used for when you will get low carbon dioxide pressure. If your carbon dioxide pressure availability is high, you go for physical absorption. But advantage with chemical absorption is that it dilutes CO2 effectively. Therefore, there is no question of CO2 removal. The removal is effective. Another is like physical absorption process is energy efficient. So there are both pros and cons with chemical absorption. Depending upon the scenario, you can choose. Next is like cryogenic. Your cryogenic capture technology. So in cryogenic, what happens? You cool and compress the gas to force it for phase change, and in this way you can go for a very high carbon dioxide recovery. The purity of carbon dioxide will be very high. Here, no use of chemicals and very easy to transport. So there is an advantage of cryogenic capture technology. Next is a membrane separation. Now in membrane separation, it employs a thin semi-permeable membrane, maybe polymeric membrane, maybe natural membrane, that divides gases into permeate and retent streams using either pressure or temperature or electric forces. This membrane separation technology is very compact and durable and allows a controlled gas flow. Then there are technologies like adsorption. Adsorption is a very high capacity, automated, simple operation technique, and therefore very promising for removing carbon dioxide from industrial flue gases. Last but not least, it is a chemical calcium looping. It enables inherent CO2 separation either using metal oxides or calcium looping technology. It is cost effective, and if you go for calcium looping, it may increase the plant efficiency. So these are several CO2 separation technologies. Now, depending upon its merit and situation, you can go for any one of the technologies. Now we'll come to utilization. So utilization is like, you if you have any avenues to utilize the CO2, carbon dioxide, and convert it into useful product, so it provides both emission reduction as well as resource generation. So utilization is very important. Like, you can capture CO2 and then transform it into some synthetic fuels, some chemicals, like you can make a medical grade calcium carbonate, or building materials like some concrete like structure materials you can make, which will offering economic benefits as well as will be treated as avenues to reduce emissions. We'll discuss some of the way to use carbon dioxide and convert it into some useful materials. One is like synthetic fuel. You can use carbon dioxide to convert into synthetic fuel, which can replace the fossil fuel, reduce emissions, and promote a clean energy future. Next is construction materials. You integrate CO2 into cement, concrete, and other materials, lowering the carbon footprint of these materials. A study shows that concrete alone can embody 45 to 55% of carbon. There is an university, RKDF University in Bhopal, India. It has collaborated with CSR India on CCUS and Green Hydrogen Initiative. So they are focusing on utilization. There are various academic organizations, and they are incubated. They are incubated startups. Those who are working in the utilizations. I will defer some of this in later slides. Next is like chemical and materials. CO2, you can convert CO2 into methanol. Methanol is a key building block for making plastics and other products. Next one is, you can create polymers, composites, and other value-added goods from captured CO2. Another thing is like mineralization, where if you cannot do anything with CO2 on surface, you can think of storing the CO2 into subsurface for some years under heavy temperature and pressure, where sequestered CO2 will be subsequently crystallized into some minerals like stable carbonate forms. So it is like permanent solution, and you can use that crystallized form of minerals for commercial use. Next is agriculture and food. You have seen the greenhouse effect, especially in the regions where sunlight is not abundant or temperature is not above 20 degree throughout the year. They grow plants and foods in greenhouse. So because carbon dioxide is harmful for us, because it is a food for plant and trees. So captured CO2, it can improve in crop growth in the greenhouses, boosting agricultural productivity. You can use CO2 as a base for fertilizers, contributing to more efficient farming. In the fertilizer production, you can use CO2. Even a lot of fertilizer companies, I will give you some of the examples of Indian fertilizer companies. They are using CO2 for fertilizer productions. Then food industry applications. One is like we all like carbonated beverage. Also, although we know that carbonated beverage are not healthy for our body. So carbonated beverage is like you just punch the carbon dioxide into the beverage to make it say like soda like drink. And if you do it, it will not only convert your water into soda, but it will extend the product shelf life. So, so food industry can also help us in taking some of the captured carbon dioxide. Now, carbon dioxide can also helps in the growth of microalgae. Microalgae can be converted into biofuels, animal feeds, or some valuable chemicals. So when you convert microalgae into biofuel, so this will eventually reduce the reliance on your traditional fossil fuel. Wherever possible, I will give you some examples, uh, Indian examples, so that you will have an idea in the CCUS technology where actually India stands. So National Aluminium Company NALCO, it has established a bio-CCS based plant in Angul, Odisha, demonstrating this potential. Another is like those who are working in wastewater. Flocculation is a step to clean the waste, to clean the solid particles in the wastewater. So if you go for flocculation based CO2 capture, so this is also an emerging area. Next one is like sequestration. If you cannot do anything useful commercial with CO2, what will go? What will do? You cannot store it on surface, because storage in a cylinder for long period of time is a cost effective affair, a costly affair, as well as it is like a time bomb. So you cannot store anything on the surface. So subsurface storage, or in other words, storage of captured carbon deep into the earth. So that is one of the objective. So now where you can store? One is like okay, wherever a oil field or gas field is opened for commercial exploitation, it has a certain life, and after spending that life, the commercial exploitation of oil of gas into that oil rig is not viable, commercially viable. So companies usually leave that oil or gas rig, known as spent oil or gas rig. So still some percentage of gas or oil are there. So if you can use this carbon dioxide to inject around this oil rig, then beneath the surface, it will create a pressure on the leftover gas and liquid, and therefore it will be economically viable to take out the leftover gas or oil from that spent oil rig. So there are ways. We'll discuss more about sequestration now. So one of this is known as enhanced oil recovery. You have CO2, you inject it around the spent oil rig, and thereby increasing the pressure. And as the pressure is increased of the liquid, so liquid will obviously will come out. So boosting oil production from the existing oil or even the spent oil. Another is store CO2 underground, maybe in saline aquifers, because there are two types of aquifers. One is your sweetwater aquifer, which we use for our drinking water, and another saline aquifer where brine is there. You can mix it with brine, but when you store carbon dioxide in subsurface, it has both advantages and limitations. So these advantages and limitations require careful evaluation for a sustainable implementation. Otherwise, what will happen? The carbon dioxide leakage will start, and locally it will pollute the environment. Now, let me share with you some of the Indian success stories. TACFL, a company located in Tuticorin, they partnered with Carbon Clean, a UK-based company, and they run world first industrial scale CCU plant near Chennai. It is installed on a coal-fed boiler. The plant is designed to capture 60,000 tons of CO2 per year and convert it into soda ash. The project is fully financed privately, and the cost is estimated to be just $30 per ton of CO2, which is much lower than 60 to $90 per ton of CO2 typically observed in the global power sector. Another is a success story where a startup incubated at IIT Bombay known as Urjanovac. It enables facile conversion of CO2 into commercially high value products like pharmaceutical grade calcium carbonate. So these are two Indian success stories I shared to you. Now there are a lot of research going on. If the technology can be developed to generate solid carbon from carbon dioxide gas in near future, then the use of carbon dioxide would be diverse and the value chain would be improved a lot. So chemists are already working on it. Now come to different carbon sequestration method. where we'll explore the scalable technologies. The scalable technology is very important. You can develop a technology in your lab for 1 gram or for 1 milliliter of solid or liquid or gas. But whether your technology is capable of scaling it so that you can use it for industrial scale. If it is not, then your technology will be confined into lab or within the patents. So there is a company known as Equinor. It is a Norwegian company. It runs Northern Lights, which is the most successful CCS projects, carbon capture and sequestration project to date. So yes, there are a few success stories. India is gradually catching up, but the Scandinavian countries, the countries in the northern hemisphere, towards the pole, like Norway, where you see it is expected that the countries near the northern pole, so they will face the consequence of global warming fast, followed by the other countries. So they are desperate to use the technology like CCUS, because CCUS is a technology which has the ability to make this world a carbon neutral and in some cases carbon negative. So I can share your data. I can share your data like CO2 capture and storage is there for data is like, if you see the potential of CCUS, a study shows that 19% of the around 20% of the required reduction of greenhouse gases emissions by 2050 will be done by different carbon sequestration method. So you cannot really neglect carbon sequestration just by saying that this is not economically viable now, this is quite costly. So now see, in deep unminable coal beds, there are coal beds which are used for coal mining, and after that they left it, and there is no use. So this kind of coal beds you identify, and if you inject captured carbon dioxide into the coal seams, which will displace the methane trapped into it, and therefore you can recover methane and which can be used as a fuel. So this technology will give you two solutions simultaneously. One is your CO2 is getting stored and you are recovering methane, thereby some additional energy will get in this process. This is known as enhanced coal bed methane, ECBM. Okay. Now, if you use CO2, again, I request the participant to please mute. All the participants, please mute from your side. The CO2, the captured CO2, if you inject it, it can boost the methane recovery up to 90%, which is significantly higher than the conventional method. Next is like whether your project of like ECBM would be technically feasible or not. That depends on the coal permeability. Permeability means if the gas passes through a particular coal seam easily, you may call it is more permeable. So it depends on coal permeability. And coal has a very high affinity for CO2, therefore allowing permanent storage
मनी
while
हल्का
methane production.
थोड़ा अच्छा से चलियो रहा है। अरे उन्हें तो कहिए से प्रॉब्लम है और सब पे तो वाईफाई भी लगल है ना।
I request the participant to please mute at this stage.
लगल है।
Please.
हाँ। सब में
I request the
लाइकॉन
host
हॉस्टल
please
जाओ
mute to please
वापस जाओगे तो
help to mute
Participants,
लाइकॉन वाला भी है।
participants,
I think you have a control.
Vijendra Pratap, participant Vijendra Pratap, please mute yourself. Okay, sir.
Okay, thank you. So now see, if you see the coal-fired power plants in our country, so most of the coal-fired power plants are located near the coal mines. So if you go for this ECBM technology, this method reduces the carbon dioxide transportation cost because you just capture carbon dioxide from the nearby coal-fired power plant and sequestrate it into the coal seams of the unminable coal beds and take out the methane. So this type of technology is possible in eastern part of India, where you will see mostly the coal-fired plants are located very near to the coal mines. A study shows that 30 to 60% more crude oil can be extracted using CO2 based or enhanced oil recovery, because in the spent oil rig, when you inject CO2, this CO2 will mixed with oil and it will reduce the viscosity of that mixture, and therefore you can transport the oil, which will become cost effective. A data shows that globally, if you use CO2 based enhanced oil recovery, it can yield 470 billion barrels of additional oil and store 140 billion metric tons of CO2, which is equivalent to, means whose contribution on the atmosphere is equivalent to the greenhouse gas emissions of 750 numbers of 1 gigawatt size coal fire power plant over 30 years. So you see the huge consequence of employing CO2 based enhanced oil recovery. Another technique is store CO2 in the ocean, like 1000 meter depth. At 1000 meter depth, you can store carbon dioxide because ocean water is unsaturated and it can easily dissolve, and ultimately it will form a hydrate. There are different computational models which predicts that oceans will eventually absorb whatever CO2 we will inject, absorb most of the CO2. The estimated storage rate is 2 gigawatt carbon dioxide equivalent per year, but there is an environmental threat. We cannot dissolve it and starts emitting again. Now what will happen? Or if it may affect the marine lives, what will happen? So there is a lot of debate on it. Another technique is store CO2 in a saline aquifer, because you see, if the aquifer contains brine or brackish water, we don't use it for drinking purpose. So saline waters in a sedimentary rock formation or limestone formations, you will see plenty, and in the sub-oceanic surfaces around India, especially near the KG basin, near the Gujarat basin, you will see. And there, if you inject the compressed CO2, which will displace brine and occupies the pore spaces of these sand and limestone formations. So there are certain factors. We'll see it through case studies like structural quality of the sand and limestone, its thickness, porosity and permeability. It determines CO2 injection capacity. It is not like this at a pressure desired by you, you can inject it into the saline aquifer. So my student has computationally uh, simulated different scenarios and found out the pressure and flow rate at which CO2 can be injected in the Krishna Godavari basin, uh, in the coastal Andhra Pradesh, so that there won't be any leakage and CO2 can be trapped inside this deep saline aquifer. Now there are four key trapping mechanisms. One is CO2 is contained beneath a non-permeable cap rock. Sand, limestone, these are permeable. Now you see, if there is a non-permeable cap rock on the top and beneath there are sand and limestone, and if you can be able to inject the CO2 bypassing the top non-permeable cap rock, then CO2 will be injected under pressure. CO2 will be injected deep into the sand and limestone, but because of the buoyancy, CO2 will gradually come up over the years. And when CO2 will gradually come up over the years, so there is a cap rock, so it cannot come up to the surface again, even after 20-30 years. So this is known as structural trapping. Another is like residual trapping, where CO2 can be trapped as a disconnected droplets within the rock pores by capillary forces, which can prevent the migration of the CO2. I will show you some of the diagrams later where you see how CO2 migrates over the period of time, like over 10 years, 20 years, 30 years. Another is like in case of saline water, if you can dissolve the CO2 in the brine water, so it will become a part of liquid phase, increasing its density. So this is an example of solubility trapping. And another is mineral trapping. So dissolved CO2 reacts with rock minerals under very high pressure, high temperature condition, because deep below the saline aquifer, there is a high pressure, high temperature, so chemical reaction happens and it will eventually form a stable carbonate minerals. So, and your CO2 will become permanently immobilized. So there is no chance of getting the CO2 lake to the surface. But there are some key challenges. Key challenge to store the CO2. One is high capital cost. If you see the total carbon capture and sequestration expenses, carbon capture accounts for 75% of the total carbon capture and sequestration expenses. And if you deploy it in any power generating unit, it will increase the electricity prices by 30 to 90%. So That is the problem. Unless government promotes this technology with subsidy, you cannot really employ it. Next is reduced energy efficiency. CCS itself requires carbon capture sequestration itself requires energy. So where from you will get energy? From the power plant itself where you are going to deploy CCS. So it will therefore reduce the overall energy efficiency from 48% to 36%. Another is, I discussed it already, there is a potential leakage risk for CO2 through fault, pores, and or abandoned well. So therefore, request continuous monitoring. Okay. So these are the some of the challenges. Now I'll tell you current CCS initiatives in India. Pilot plants in thermal power plants and fertilizer industries, they are capturing and utilizing CO2. Like Vindhyachal Super Thermal Power Station, they captures 20 ton of CO2 daily from flue gas emanating from their power plant to produce 10 tons of methanol. So this is a perfect example CO2 capture and utilization. IFCO, you know, Indian Fertilizer Cooperative, they have urea plants in Aula and Fulpur in Uttar Pradesh. Fulpur is very near to Prayagraj, where I am located now. So they are utilizing amine-based post-combustion capture technology with a capacity of 450 tons of CO2 absorption per day. And in Jagdishpur, Uttar Pradesh, Indo Gulf Fertilizer Limited, they have similar capture technology with a capacity of 150 tons per day. So there are few success stories. Now you just look into the research and innovation hubs of CCUS in India. Department of Science and Technology, Government of India, they have established two national center of excellence for carbon capture and utilization. One is located at IIT Bombay. Another is located at Jawaharlal Nehru Center for Advanced Science and Research in Bangalore. This serves as hub for research, innovation, and collaboration among researcher, industries, and stakeholders. They also incubate startups. Apart from that, NTPC Netra, they have the facility in Faridabad. The NTPC Netra and IIT Bombay, they are studying geological carbon sequestration potential in India. So there is a shortage of time. Let me skip the policy and regulatory framework. Yes, like policy avenues, carbon credit and carbon tax. So Indian government they have two distinct policy avenues for CCUS, each with unique benefits and challenges. One is carbon credit and incentives. So if you adopt CCUS, you will get some incentives to adapt the technology, and then to run with the technology you will get carbon credits. It depends on the carbon capture. So this is ideal for decarbonizing current industrial capture. Another is carbon taxation. Carbon taxation is that if you don't adopt CCUS or similar technology, so you need to give a tax to the government, or you need to relocate the country, relocate the industry to a region it will be far from the metros or populated regions. Or if you strictly use carbon taxation, then there is a chance that few industries which are very hard to abate, they will stop their production facility or they will shift their production facilities outside India. Now, in this matter, the European Union, they have developed a cost-effective hub-based approach. Like similar technology India should adopt. You just consider a region where ultra mega thermal power plants are there. One of my students has conducted the studies and published a paper. Like near in Andhra Pradesh, very near to coastal part, Bay of Bengal, within certain distance from Bay of Bengal, there are 7 to 8 ultra mega thermal power plant. Okay. Now, if you ask each of these thermal power plant to adopt CCUS technology, it will be very difficult for them. So it will be better if you could put them in a cluster and make a CCS technology centrally, so that whatever CO2 they will generate, you capture it, transport it to a central point, utilize it, whatever percentage you can utilize, and rest you can store it in the KG basin. So this technology, hub-based CCU approach, so that is very unique approach, because these hubs will not cater to a particular industry but multiple industries at a time, and therefore this reduces the cost burdens on a single industry and makes the CCUS project viable. Now I will show you some of the case studies. Two case study I will show you. So my student Abhishek Gupta, so in collaboration with Washington University in St. Louis, USA, under supervision of myself and Professor Ramesh Agarwal from Washington University and St. Louis. So he computationally investigated the injection scenario of carbon dioxide in the saline aquifer. Okay, and he has also used some Indian scenarios like KGBC. The first case is to investigate the effects of permeability and number of layers, means the impermeable layers on CO2 migration using a single injection well. Here injection well is single. You see the case, you can see this geometry they have used is for validation. It is a Utsira formation in Norway. The green colored layer you see, so similarly they have a 9-layered model. And injection layer, you can look at it here. And what is the total domain size? The domain size is 20 meter diameter. And yellow color is signifies sand, which is porous. And there are several layers with permeability level with a certain permeability. Now it is a three-dimensional geometry. It is a three-dimensional geometry where you see the homogeneous aquifer. The length of the aquifer is like 10 meter by 10 kilometer by 10 kilometer, whereas the depth of the domain is 190 meter. Means injection happens at 190 meter depth from the surface level. Okay. Now here you see there is no low permeable layer. Low permeable layer is like it will allow CO2 but at a very slow rate. Okay. So here there is no impermeable layer. Here you just see the blue sheet. We use a blue sheet. Blue sheet signifies one low permeable layer. Here we use two permeable layer separated by 5 meter distance. Then three permeable layer and four permeable layers separated by 5 meter distance with respect to each other. Okay. Then you go for a grid generation. It is a standard CFD procedure applied. So I am not going to extend it because this is not the CFD class. Those who are interested can see because this we have published a couple of papers on this and these results are reported. So the grid independence test, we have used the grid independency test. Boundary conditions, in boundary conditions you see what we have used. We used CO2 injection rate as 35 kg of CO2 per second and our injection time is 30 years. For 30 years continuously we kept on injecting uh, the carbon dioxide. So this was the conditions, boundary conditions given to the uh, software. So it is based on you see saline aquifer. It contains brine density, viscosity, CO2 density, viscosity, pressure, permeability, porosity of sand, shale, everything is given. So these are other boundary conditions. Now we have validated it. Our validation shows that maximum difference with the result reported in literature is 22% and average difference is around 10%. For such a uh, you see the physical case where it is very difficult to simulate the case physically. So this variation is acceptable. Now what is the result? The result is, if you see the graph, so x-axis shows the volume fraction. The volume fraction of CO2 which is at 1 meter away from the injection well. You see the center line is shown as dotted. 1 meter away from the injection well is shown as a vertically you see vertically red line, and this is your aquifer depth. Our aquifer depth was 190 meter. Okay, our aquifer depth was 190 meter. So in a 200-meter scale, it is shown. If you see the graph shows the vertical distribution of CO2 plume migrated at a distance 1 meter from the center line, the at injection well, center line of the injection well. And we can see that as the CO2 is injected from here, it goes directly from the top of the surface without any interference because there is no cell, low impermeable cell in it. So smoothly it goes to the top. But what happens if you can put a low impermeable cell here? If you put a low impermeable cell, you see it will delay your injection. It will delay your injection because the CO2 will not easily percolate through this low impermeable cell structure. Now, if you add one more impermeable cell, again for CO2 it will be tough to come up So for us, were asked to prevent the leakage of the CO2 from subsurface, it is a better scenario. You just try to find out a geological locations where lot of such low permeable rocks are there between the sand or limestone structure. So it will delay the migration of CO2 plume to the top surface. So I'm sorry because I put some animations. Animations are not working here. I'm sorry for that. Yeah. Now see the case. So this is a nice graph where in x-axis time scale is shown how CO2 is migrated over a period of time, and your time scale is in year. X-axis shows the percentage of CO2 injected. When percentage of CO2 injected. Now you see y-axis. Y-axis shows the CO2 volume reaches to the top layer of the aquifer after certain year in terms of percentage of CO2 injected. Now you see at origin there is no CO2 coming out of the top layer because time is 0. Now what will happen after 5 years? After 5 years you see 20% of the CO2, 20% of the CO2 is expected to reach at the top layer of the aquifer. Whether you go for a homogeneous aquifer or aquifer with 1, 2, 3 or multiple low permeable layers. But as the time increases, what you will see after 30 years, almost 95% of the total CO2 injected, there is a chance to come up to the top layer of the aquifer. It is still in the subsurface. But if number of low permeable layer are high, the rate at which it will come to the top layers of the aquifer, that will be low. So you will get more time for leakage. Next one is surface pressures. Because you see, if you inject something deep into the surface at a very high pressure scenario, then because of buoyancy, things will come up and it will build up a pressure on the cap rock. And if cap rock cannot withstand that much pressure, so cap rock will create a leakage, and through this leakage or fissures, the CO2 will again starts coming up and will mix in the atmosphere. So your top surface pressure measurement or pressure computation is required. Now you see the radial distance, because we know we have a radial distance of about 10 meter by 10 kilometer by 10 kilometer dimension is there. Radial distance, like if you see the chord, if you see the diagonal, so it may be around 12 meter. So 12 kilometers, 6 kilometer on left hand side, 6 kilometer right hand side. So at the center you will get maximum pressure. And after 30 years, you see your pressure will be lowest. And after 3 years, your center pressure will be higher. But you have to check whatever cap rock is there, whether that 10 megapascal pressure will be sufficient to burst the cap rock. So that needs to be corroborated with the experimental results. Next one. Okay. Next one, 44. Yes. This is a very interesting one. What happens? We kept on injecting the CO2 for the first 30 years, and after that we stopped injecting. What will happen then? So under this scenario, we observed it computationally up to 80 years. Whereas after stopping the injection, we monitored it for another 50 years. And we have seen that as the injection stops, the majority of the injected CO2 eventually accumulates at the top layer of the aquifer. So it is better if you can stop injection after certain years. Okay, now we'll see the second scenario. We have still some time. It's stuck. Pushpinder? Yeah. It's okay. There is a lag. Let me. Yeah. Oh. Okay. Yeah. Now, in this case, what happens? Instead of one injection well, we'll deploy multiple injection well. Our strategy is like CO2 injection with 2 injection well, and here the total amount of injection 35 kg per second is equally divided into 2 injection well. Okay, so this is one scenario. Or we'll use 35 kg per second in one injection well for first year, and then in second year we'll use second injection well, in third year we'll again come back to first injection well. So like this. So this is like alternate injection scenario. And in second case, we proposed 4 injection wells and varied inter-injection well distance, because our objective is to keep the pressure of the injected carbon dioxide within the permissible level. So what injection strategy we can go for? So you see how inter-injection well distance are changed. Yeah. So you see the figure 31, first figure. The first figure here, it shows the maximum pressure at the top surface over a period of time. Time scale is 30 years here. Similarly, if you see figure 32, the right hand side figure, it represents the pressure increase at the top surface of earth for a single injection well with full injection and double injection well with half injection for 29 and 30 years. So if you see the results, you'll find that in case of single injection well, left hand side figure, you see the maximum pressure is reached around 3 years. So, and maximum pressure is around 10 megapascal. Okay. So it is good if you go for double injection well, and in double injection well, if you go for like half injection, means you split the injection into 2. So your pressure would be in a manageable level. Okay. Oh. Next is this slide. This is very interesting one. Here we have changed the slide distance. We have changed the slide distance, the interval injection distance. One is 5 kilometer distance, another is 6 kilometer, then 7 kilometer, 8 kilometer. You see, there are 4 wells here, 4 wells, and we have changed the inter-injection well distance. There is some problem. Yeah. So in interval comparison, if you see, if your interval distance is 8,000 meter, 8 kilometer, so it will register less top surface pressure. So that is your expected. And what is your initial pressure? Means before the injection starts, you just see the horizontal dotted line, but that denotes your initial pressure. Now you compare it like increase of center pressure. You see, as you increase the central distance of injection well, your increase of center pressure will be reduced. So it is better if you increase the central distance of two injection well. So with this, I want to conclude. So the maximum what we have seen from these two case studies. Also, we had to hurry up because there was less time left. So I could not really elaborate the computational methodology part. I just explained the problem and immediately showed some of the results. So the conclusion from the result is the quick summary is the maximum pressure buildup at top surface aquifer occurs when you use a single injection well, and if you use a double injection well where you just divide the injection rate, split the injection rate in these two, so you can reduce 40% pressure. So that is a good scenario. Next is like if your inter-injection well distance is 8 kilometers, so it gives you optimal result in terms of pressure buildup. But what you need to study is the environmental impact. Nowadays, any big, large industrial projects cannot get clearance without the environmental impact assessment. So, environmental impact assessment of CO2 injection must be studied. Even if it is implemented, environmental impact of CCS project must be monitored and managed even after stopping the injection, because CO2 is a gas and gas rises, and this is not a gas under high pressure, high temperature. So CO2 plume continues to migrate inside the earth's surface. You cannot see it, but it happens, which creating more interference at the top surface of the aquifer, and whenever it gets a passage, it will come up and it will mix with the atmosphere. So with this, I close this session. So over to the organizer. Let me stop sharing. Yes. Over to the organizer.
स्ट्रेस एक तो प्रेशर स्ट्रेस जो बढ़ रहा था,
Yes.
कैसे सर स्ट्रेस कैसे ट्रैक करेंगे आप?
आप फिर से बताइए, प्रेशर स्ट्रेस जो बढ़ रहा था।
हाँ, एक प्रेशर स्ट्रेस जो था, यानी स्ट्रेस यानी इंक्रीज ऑफ CO2 प्रेशर एंड
प्रेशर,
स्ट्रेस।
हाँ प्रेशर, प्रेशर, हम प्रेशर के टर्म में, प्रेशर pressure determination is required because CO2 leakage occurs due to the buildup of pressure over a period of time. It is like when you sequestrate, when you inject any gas inside the rock, what happens? You are basically making a gas bomb. वो कभी भी फूट सकते हैं. What is the use of CO2 injection deep into the rock if it comes out after some time? We are, the best scenario is that the most of the CO2 injected deep into the rock
Yes.
should not come out. It will be trapped forever. Whether it is mixed with brine, whether it is mineralized with some crystal in form of some crystallized structure, it should be trapped. Even if remains in gaseous form, it should be trapped. It should be trapped, and it will be trapped if the local pressure doesn't increase the fracture pressure of the rock, the fracture stress of the rock. So you need to calculate the pressure, you need to simulate the pressure build up over a period of time and match it with the pressure which requires to fracture the particular rock. Okay, this is for safety purpose. Otherwise, what is the purpose of using CCUS? Okay,
Thank you, sir.
next.
Thank you, sir. We sincerely thanks Professor Akshay Ranjan Paul for his enlightening session on decarbonizing the atmosphere using carbon capture, utilization, and sequestration, challenges and opportunities. Today, he has described what is carbon capture, utilization, and storage. He also explored innovative solution to reduce CO2 emission. He also described about the different methods for carbon capture and various challenges associated with it. He has also described how we can utilize CO2 so that it has reduced effect. He has also explained sequestration and its various methods. So he also told us some Indian success stories. He also described about CO2 trapping mechanism. He has shown some of his research results on, also described various case studies. With all these discussions, we will have a better understandings. His deep expertise, extensive research, and look forward to his perspective, having provided us with the valuable insights into the informative pathway. With this, we conclude session 10 of our faculty development program. On behalf of the organizing committee, we extend our gratitude to all the participants for their keen engagement. Thank you, sir. We look forward to meeting you tomorrow for the final day of our FDP journey, which also includes a test session at the end.
When the test will be conducted, ma'am? Because I need to send the MCQ questions.
Sir, tomorrow there will be test session.
At what time?
Yes, sir.
At what
Sir,
time?
7 to before 6 o'clock.
Okay. I'll send it to
Okay.
by noon. Okay, thank you.
Okay, sir. Tomorrow there will be a test session. Please note that this test is compulsory and the participants must score at least 70% marks to receive their certificate. There will also be a feedback session where participants can share their experience and views related to this FDP. Thank you. With this, we are concluding today's session. Thank you. Good night.
Thank you. Thank you.
Thank you, sir.
Thank
you, ma'am. Thank you. Thank you, sir.